This video is going to explain the crucial steps in ion identity networking and then the whole workflow for the article. And for this, we're going to use the batch mode. So we open up the batch mode and load the minimum requirements for ion identity networking in a batch file. And here we can see that we only have to take 2 steps before we submit the data to GMPS and Sirius. And the 2 steps are meter correlate for feature grouping and ion identity networking to identify the different ions of the same molecule. And right now we don't want to do GMPS and Sirius, so I'm just going to remove these 2 steps. And if we take a look into meter correlate, we can see we just use the retention time tolerance and the correlation grouping to group features. And you can find the settings in the batch file that I supply, and also try this on your data set. And for ion identity networking, if you open this up, you can see that we have the ion identity library, and the ion identity library is here, and it's a very basic library. So we only allow a maximum multimer count of 2. So we only allow 2M plus sodium, 3M, and don't 3M plus sodium, and so on. And then we have only the basic adducts. So we only have the protonated sodiated ammonium adduct, some doubly charged adducts, and some adducts that I know very often occur in my data set. So you definitely have to change this for your data set. And then we allow some in-source fragmentation of water losses. And so if we directly apply these 2 steps to the aligned feature list, so we apply this, and the feature correlation grouping is already done. So we already have a new feature list here. So the feature list I used for these 2 steps was the aligned peak list that I filtered for duplicates, and I also filtered for isotope logs. So a minimum isotope pattern of 2 peaks. But you can choose any of these feature lists and any filtering steps. And so now we end up with a feature list where we have ion identity networks, and we can sort by the network ID. And here we can see that we have plenty of ions, but they are limited to all the different ions and in-source fragments that we allowed. And in this way, we can make sure that we end up with very good networks. So we only have networks with the protonated, sodiated, and so on adducts, some in-source fragments and multimers, and we don't see any weird combinations of adducts and in-source fragments. But now in another step, and this is why we made it so modular, now in another step we can add more and more different ion identities. And so if we go to identification and ion identity networking, you can see all the different modules that we're going to apply. And so if I go back to the feature list, and now I'm going to open the batch mode again, load the full workflow, you can see that we have a lot more different modules here. And this is what I usually do. So I usually apply a peak filter to get rid of some bad shaped peaks. Then I apply the duplicate peak filter, which is totally optional, and the peakless rows filter. This is basically to get rid of features that don't have any 13C isotope pattern. And then we do meter correlate, ion identity networking, and some more steps. So if we clean up the filtering steps here, so we're not going to use the filtering steps. Meter correlate is the same as before, and ion identity networking is also the same as before. So we have the same adducts, the same multimer count and in-source fragments, but we don't apply any annotation refinement, because now we just want to use add ion identity networks to add more and more of the non-commonly seen adducts. Because in some chromatography systems, you might see some iron adducts. If you work with biological samples, you might see some calcium adducts. And so in the first step, I add all the different adducts here and no in-source fragmentation. And you can go up here to a maximum multimer count of whatever. And these additional ion identities are only added to existing networks. So we already made clear and sure that we only create networks with good ion identities. And now we add more of the uncommonly seen adducts. And here I just add more in-source fragmentation. So we have 3 water losses, 4 water losses, ACN, and formic acid. And then only some of the adducts that tend to form in-source fragments. And in this way, and with the ion identity network refinement, so we're going to get rid of this and that and this. So this is the bigger full workflow that we're going to apply for the article. And here we can see that the ion identity network refinement is just going to delete all the networks that have less than 3 ion identities. And this is very important to be sure that the ion identity networks are correct. I mean, if you have a data set where you only see protonated and sodiated adducts, you should definitely not use the ion identity network refinement here, or just set the minimum size to nothing. But we're gonna just use it to make sure that we only look at good ion identity networks. And now we apply this to the whole thing. And I already did this, so we have the minimum settings here and the full settings. And if I just look at the number of ion identities, for the minimum settings, we only found 179 ion identities. And with the full settings, we found 253. So we added a lot of different adducts to the whole ion identity networks. And we can actually see it here. Even if we sort by the ion, we can see that we have a lot of different in-source fragments here. And the in-source fragments are limited to the protonated species, which is usually the case. And then we have, if we go down, we also see some calcium adducts. We also see some doubly charged calcium adducts and iron adducts. And so we can see that we cover more of the different adducts. We cover a greater space of the mass to charge ratio, as some of these adducts are a lot bigger, as for example with the multimers. And so now we have bigger networks. And this is why we apply multiple steps here. So this is why we apply ion identity networking and then add ion identities to networks.